and squared, and also iCred for the opportunity to talk today. And thank you to our wonderful staff for facilitating everything. Everything's going great so far. Really enjoying it. So my slides are available via that QR code. I probably won't get through everything, even though I have an hour and a half. It is a long time. I mashed the tutorial and research presentation together. So to relieve the monotony of my voice, please jump in, ask questions, interrupt me, and we'll have a better time that way. So just a little bit, well, first of all, let me give an advertisement. This talk is based on a contributed chapter to this book. I'm co-editing a book with Wei Wang and Juliana Simchin, and I contributed a chapter myself. This book has 17 chapters from people across active colloids field. We have the basics of active colloids, details of model systems, theory, and frontiers. This book is due out hopefully in December, so just in time for Christmas. Get it for your friends and family. I do get a small percentage of the sales, but that's not material, it's immaterial. So this is based on that contributed chapter. Okay, a little background on our group at University of Hawaii. Many of you have already met Viviana. She was in Hiroshima for the site visit in September. At the time, my wife and I were having a baby and I wasn't able to come. And I heard she did a great job representing us. So we have a multi-scale approach. We have 3 corners to our general approach here. In this corner, we have high-resolution microscopic modeling of active colloids. So active colloids, as we'll discuss, are particles that can swim in liquid media. And in this corner, this is really our expertise. We model the active colloids in a high resolution with microscopic detail. We resolve their geometries, we resolve their swimming actuation, we resolve the fields that they source, like the flow field you see here in the background. And this inherently involves solving partial differential equations, as you'll see. We can do this analytically or numerically, but it's a little bit limited in how many particles you can do. You can do 1 or 2 or maybe 10. So increasingly, we're moving into coarse grain simulations, basically active Brownian dynamics with active hydrodynamics. And what we're trying to do is have a bridge between these 2 levels. So we parameterize the coarse grain simulations from the high resolution calculations. And then if we see something interesting like these clusters, well, then we can go back to the high resolution models and look in further detail. I also have a small experimental lab that I started 2-3 years ago. We've had some success, we've made particles, but I will say, coming from theory computation, experiments are hard, and publishing experimental data is even harder. So I benefit from many great collaborations on the mainland of the US, in Europe, and hopefully also here. So if you're interested in talking about doing these experiments, please come up to me later today. And we have 3 current graduate students, and I said you met Viviana, and I've graduated 1 student already. Okay, so what is an active colloid? As I said, microscopic particles that can swim through liquid. And this whole field kicked off in the early 2000s in the work of Wally Paxton and the Sen group. They made these bimetallic nanorods, so maybe 50 or 100 nanometers diameter, micron in length. I don't remember the exact dimensions, but these are made of platinum and gold, and when you put them in hydrogen peroxide solution, they'll catalyze the decomposition of hydrogen peroxide into water and oxygen. And this is a redox reaction. Both ends participate in the reaction. So you have an electropotential difference in the solution that drives hydrogen ions from one side to the other. And these hydrogen ions also drag fluid with them. So we have fluid flow resulting from the consumption of chemical free energy that's converted into mechanical motion of the fluid. And that leads to swimming motion of the particle. So if you drive fluid past you in the pool, you move forward. So does this freely suspended nanorod. Now, these are very hard to make. That's my understanding. So this system has become more popular. These are easy enough that we've made them in Hawaii, platinum on silica or platinum on polystyrene spheres. What you do is You buy spheres from a supplier, silica spheres. You plasma clean a glass slide. You drop, you put a drop of these silica spheres suspended in water on the slide. The drop will spread out, wet the slide. You'll get a nice monolayer of spheres. And then you can sputter coat the metal from above. Most microscopy facilities will have a sputter coater that's available in most places. So they're very easy to make. And I would say, I guess it was the House and Evans and Golstanian who first made them around 2007. These also move when you put them in hydrogen peroxide. Initially, it was thought that they move in self-generated oxygen gradients because you don't have, well, you only have one metal, so it seems like there shouldn't be a redox reaction. It's been a little controversial since then. Now people are arguing about what's the mechanism, but it's been a workhorse of the active matter field. I really like this mechanism. This is not chemical. This is strictly electrokinetic. So you can take your metal on insulator Janus particles, doesn't matter what metal it is, doesn't matter what insulator, put them in an AC electric field, and what will happen is the metal will polarize, as we know from freshman physics. You'll get charge separation, positive charge here, negative charge here. And this is for the half period shown where the electric field is down. Well, these guys are not in a vacuum, they're in liquid. And liquid water has ions. So this surface charge will attract ions that neutralize the surface charge. So now you have these induced double layers. And the electric field will act on the mobile ions in the induced double layers, driving them from the equator to the pole. So we have transduction of electrical energy into mechanical motion of the fluid. The ions, as they move, will drag fluid with them. So you have this interfacial pumping, and the particle will move away from the metal side. We've also made them, we've seen them move. You just need to make a little cell. Sorry, it's kind of obscured here, but you have a little cell and a function generator between them, and you can watch them move. So I like this picture because you can really see that the actuation, the swimming mechanism, is interfacial, right? All the, what's generating the swimming motion is happening in a thin film at the particle-liquid interface in the induced double layer. So these are all interfacial swimmers, interfacially driven active colloids. You have, in each case, a gradient of some field. Here it's the electrical potential. The gradient of some field is driving an interfacial flow with some material-dependent coefficient. So for this guy, it would be the induced zeta potential. For these guys, the B is what's called the phoretic mobility. But yeah, in each case, you have flow due to surface gradients of some self-generated field. This mechanism is a little more complicated to explain. If you're interested, I can circle back to it. The electrokinetic swimmers I like better in terms of explanation. Okay, so let's watch them move under the microscope. These are the chemically driven swimmers. The black is platinum, the white is silica. This video was taken by my collaborator, Jaideep Katuri. And looking down through a microscope, they're moving above or in the vicinity of a glass slide beneath them. The particles are heavy, so they sediment to the glass slide, and they move in 2D. And you can watch them. They tend to move away from the platinum cap. Sometimes they encounter each other, have some interaction that redirects their motion. If you watch one who's by himself, okay, the video stopped, but if you watch one that's by itself, it will eventually change its direction of motion. Let's watch this one. Because these guys are weakly Brownian. They're 5 microns diameter, and over time, he'll change his direction of motion by rotational Brownian motion. So this is nice, and if you think about it for a while, there's something curious here. The curious thing is that we have a metal hemispherical shell, 5 or 10 nanometer thickness, on silica. So these guys are bottom heavy, right? You should see the metal oriented downward. You should actually see all black because the silica is transparent. So you should see all black if the metal caps are downward. But we see always the metal caps are oriented in the plane of the slide. You see half black and half white. So that was what really got me into the field. Miko I don't know if he's here yet, Miko, he's in the center. In 2013, 2014, he hired me as a postdoc. We looked at this problem and we figured out, or proposed, shall we say, that when you have chemical activity, you have interactions of the particle with the surface, hydrodynamic interactions, chemical interactions that lead to this orientational locking of the particles in the plane of the glass slide. So this is a side view and that's a top view. Sure, oh, absolutely, yeah. This, if you watch it, it seems very weak. If they are in the close vicinity, they hardly seem to perturb each other. So that's, I guess, been a puzzle. You would expect long-range interactions, 1 over R, from creating, each guy creates a chemical field, but yet they seem to, at least in this video, only weakly interact. And they seem to act like active Brownian particles that only interact sterically. Yeah, maybe these guys, maybe if maybe they're getting stuck between the metal caps. I think other material systems, so you can use other catalysts. We've used in Hawai'i gold palladium. It also moves in hydrogen peroxide. I think other material combinations may have stronger interactions. Juliana Simchin actually had a nice paper about this in Small recently, where they looked at particle-particle interaction. So I think it would depend on the materials and also on the reaction mechanism, whether you have long-range chemical interactions between them. To get back to your point about sticking, generally not a problem. We found, we did little experiments in Hawaii, not a problem for the chemical ones. For the ICEP, we have a big problem with sticking because we have electrodes and the particles are attracted to the electrodes. We're trying to put in surfactants to stop the sticking. Seems to be working okay. Some people put a little layer of silica on the electrodes to try to stop the sticking. So apparently that's a big problem with ICEP. Sticking is a huge problem. Other people I talk to say it's a huge problem. These guys, I don't know, not such a problem, maybe except when they get close to each other. So back in 2015, we looked at this problem of an active Janus particle near a hard planar wall. And you see here that the product is confined between the particle and the wall. So you have an accumulation of the reaction product here. And you also have flows that are created by the particle. These flows are reflected off the wall back to the particle. So it's like if you're swimming in the pool, you're creating flows. And if you're near the pool wall, you'll feel an effect of that pool wall analogously. So this guy can sense the presence of the wall through the distortion of the chemical field and also in the distortion of the flow field by the wall. And this is what we, in that paper, found induces kind of an attractor, a 90-degree or nearly 90-degree attractor for the particle orientation. It's attracted to the sliding state where it has a fixed height above the wall, a fixed orientation, and moves along the wall. So that's the kind of thing in general I'm interested in. Understanding how the fields sourced by a particle lead to complex motion in complex environments, how they can navigate in complex environments through these self-generated fields. Okay, so getting more into the tutorial part. You may ask, we have so many swimmers and flyers in nature, what do these guys resemble? So I put up 6 different swimmers. In the top row, we have macroscopic sized. Bottom row, we have microscopic sized. And I suggest that our synthetic Janus particles are most similar to these. They look quite different. These guys are covered with thin cilia, carpeted cilia. But those cilia also pump the fluid around them. They wave, as we'll see, in a periodic way, the pump fluid in a thin layer around the particle. So from a modeling perspective, these are actually the closest to our synthetic Janus particles. Interfacial pumping. One thing I like to ask my students in graduate fluid mechanics, why is the penguin streamlined and this guy obviously not streamlined? We're going to get into the basics of low Reynolds number fluid mechanics and we'll answer that question. None of these guys looks very sleek or streamlined on the microscopic scale. Okay, so here is your crash course introduction to low Reynolds number fluid mechanics. Up here on the top, we have the very basics. We have ma equals F, but in disguise. So this is basically Newton's second law, but when you take an Eulerian point of view, when you think about fields, the velocity field U that varies in space and time. Some of you may know this already. A lot of people working in liquid crystals here. But this is really ma equals F when you're not following one particle, but rather thinking about fields. And by convention, the acceleration is written on the left, hence ma equals F. On the right, we have sum of forces. We have pressure gradients, and we also have viscous stresses. We have a Newtonian fluid like water, so we don't have a liquid crystal or anything fancy like that. And this is the Navier-Stokes equation. Okay, so you can find the detailed derivation in textbooks. Basically, you look at a blob of fluid, you do a force balance on it, then you shrink the blob to a point, you can get that equation. Okay, so when you're confronted with a PDE like that, one of your first instincts is to non-dimensionalize it. Right? Every term here has dimensions. So what we can do is go to the problem we want to solve. We want to solve for the motion of a microswimmer, and we can use characteristic quantities from that problem to non-dimensionalize various terms in this equation. The tildes indicate that they're dimensionless. So to get dimensionless velocity, I take little u, divide by big U, I get U tilde. Pretty straightforward. U is the velocity we want to find. L is the size of the microswimmer, and this guy is a model bacterium who's actuated by a spinning helical tail. Well, there's your chirality. So we have an intrinsic timescale inverse omega in this problem. Okay, so you can use all that. You plug it in, you get this equation, dimensionless Navier-Stokes. And out pop the dimensionless groups, Reynolds number, and oscillatory Reynolds number. The oscillatory Reynolds number happens or appears when you have this kind of intrinsic timescale. If you didn't have an omega, that you could just use L over U as a timescale, you'd get Reynolds number here as well. Okay, this is great because these dimensionless groups can be used to quantify the relative importance of terms in your equation. And they have physical interpretations. So you look at the Reynolds number, on top you have rho UL. Well, rho has something to do with mass. Rho U is momentum. On the bottom you have mu, viscosity. So it's inertia over viscosity, the relative importance of inertia and viscous shear stress. Okay. You can, and Eric Lauga did this in his wonderful textbook, look up these quantities for various swimmers, plug them into those dimensionless groups, calculate them, and you find a very wide spectrum of these groups from 10⁻⁴ Reynolds number for a bacterium to 1 million for a penguin. So that tells us that bacteria and penguins encounter very different fluid mechanics. For a bacterium, viscosity dominates inertia. Inertia is negligible for bacterium. For penguin, it's the other way around. Inertia dominates their fluid mechanics. So we can potentially get rid of the whole left-hand side for our microscopic swimmers. We can say Reynolds number is small, oscillatory Reynolds number is small, and that's great because we'll see that gets rid of the very pesky nonlinear term appearing in the second term here. Now, oh, by the way, if you're interested in technical details, you may ask, what about this pressure scale? This is not obvious to me, so how did I come up with this? When you non-dimensionalize the equation, and you say that P tilde is P over some unknown P naught, you'll get over here P naught L over mu U, and that will tell you immediately, oh, okay, a natural choice of P naught is mu U over L. characteristic viscous shear stress. That's a natural choice for these microswimmers. You may have also seen elsewhere rho u squared. That would be a natural choice for the penguin, because if I divide both sides by Reynolds number, I would get inverse Reynolds number, and I want to keep the pressure term, so I'd have to choose a different pressure scale that makes this term order 1. So this is the appropriate stress or pressure scale for a small swimmer, and rho u squared is appropriate for a large swimmer. Yeah, pressure is a little special because it's there to enforce this incompressibility condition. I'm going to consider incompressible flows, no sources or sinks for the fluid flow, and so pressure is there to enforce that. Okay, so we've concluded we can throw away the left-hand side, get rid of this nonlinear term that's the source of all the problems in turbulence and high Reynolds number fluid mechanics. We get a nice linear equation, and not only linear, but time independent. That's wonderful, because I don't know about you, but I never want to solve nonlinear equations. Linear equations, you can bring in all the machinery like Green's functions, superposition principle, etc. I only want to solve linear equations. If you give me a nonlinear one, I'll try to linearize it. Okay, that's great. On the other hand, your intuition is developed for big swimmers like penguins. So whatever you think you know about swimmers, if you're not in this field, is probably wrong when applied to small swimmers. So we need to redevelop your intuition for flows governed by the steady Stokes equation, as this is called. So I'm going to help you do that if you're not already familiar with this. We're going to start with some intuition pumps or some thought experiments, where I'm going to do purely qualitative arguments to show you that linearity gives you some physically significant results. So here's a common problem in low Reynolds number fluid mechanics. We have a sphere that's sedimenting near a wall. And we ask, what's the velocity of this sphere? Well, of course, it's going to sediment downwards with gravity, but is it going to move towards the wall or away from the wall? I can show you, without any math, that it will move straight down. How do we do that? Well, we know linear systems are linear in the driving forces. We'll use that point. But first, let's just rotate our coordinate system. That's a perfectly legitimate thing to do. And look at the falling sphere from the other side. I just rotate the coordinate system around the wall normal. So you get gravity pointing up and the arrow pointing up as well, the velocity arrow. Now I'm going to exploit linearity. I'm going to say if I were somehow able to reverse gravity, the response of the system, which is linear in the generalized driving forces, should also reverse. So if I were able to reverse gravity, the green arrow would reverse. It would pick up a negative sign. And now I've obtained this picture. And you look at those two pictures, which were both legitimately obtained, and you say, how can I reconcile these? The only way I can reconcile them is if there's zero wall normal component of the velocity. So we conclude that the sphere will fall straight down, no drift towards the wall, no drift away from the wall. This is the kind of argument people love to do in low Reynolds number fluid mechanics, and it's also an important result for microfluidic devices. So microfluidic devices also have low Reynolds number flows, and people want to manipulate particles. They want to move particles around. And this is telling you that if you have a sphere in a microchannel, don't count on a wall effect to get it to move away from the wall. It's just going to move straight down under gravity. And you can think about, how can I change up this picture? Maybe you can make the particle non-spherical. What happens then? Well, then we can no longer do this kind of exploit this axisymmetry, and the argument may break down. So lots of fun to be had purely by qualitative arguments. Another consequence of linearity, I asked, why aren't paramecia streamlined? So here we have a nice streamlined or streamlined-ish shape, and we have a flow coming from the left. I drew the drag force. You would expect, okay, if this is nicely streamlined, if I reverse the flow so that the flow is coming at the blunt end, I would get a big drag force in that configuration. But we know we have a linear system. I reverse the driving force in a generalized sense, so the external velocity. I would simply reverse the drag force and get identical magnitude but opposite direction. So streamlining has no advantage at low Reynolds number, and that's why these bacteria and other things don't look very sleek. Okay, one more introductory slide. So you've probably seen Stokes' law before, the drag law for a sphere at low Reynolds number. And there's a very long derivation of this that takes 4 pages. You have to use the Stokes stream function. I don't want to use that machinery. It doesn't generalize very well to other things. And I don't know, it would take a lot of time. We can get everything but the 6 pi very easily, because we already worked out the characteristic shear stress or pressure, characteristic stress. And we can say, well, by scaling arguments, the drag force should go like the characteristic pressure, and I need to multiply by an area to get a force. And indeed, you get something that goes as mu RU. You get everything but the 6 pi. So I'm going to skip over that whole derivation of Stokes' law. To get the 6 pi, you can look in a textbook and work through 5 pages of algebra. We also have a Stokes drag law for rotations. Again, you just use the characteristic stress. For velocity, use omega r. And because we want a torque, we multiply by r cubed instead of r squared. And you get everything but the 8 pi. Okay, so that's great. And as you expect, everything's linear in the translational velocity and rotational velocity. It's all quite nice. But this is a little boring because the sphere looks the same in all directions. So let's build up to something more interesting. Let's look at a spheroid. So I have an oblate spheroid on the left, prolate on the right. Well, here again, we can use linearity. If I have a velocity in an arbitrary direction, not shown, but if I have an arrow like this, well, then I can decompose onto the axis parallel direction, and I can also project out the axis parallel direction by this kind of math operation. I can calculate the drags separately for those 2 problems and then superpose them. So very easy to obtain everything but the coefficients here. Maybe we can get mu and r by scaling arguments, but the numerical prefactor, we'd have to do some difficult math to get that. Although we expect, of course, that zeta perp is going to be bigger than zeta parallel. And the same goes for the angular velocity. So maybe this is all kind of common sense to you. So let's do something even more difficult. Let's look at, and we're in a chirality and not in this workshop. Sorry, I don't have any not in this, but I do have a chiral thing here. Let's look at this micro screw and this micro propeller, these nice chiral objects. And here we have translational rotational coupling. Because okay, let's look at this micro propeller. If you have it moving in the y direction, this disk that's moving edgewise on, small disk moving edgewise, would have a small drag force on it. And this disk that's moving broadside on would have a big drag force on it, right? It's kind of intuitive. So you would have small drag force here, big drag force here. You would get a moment on the particle, i.e. a torque. So a translational velocity would produce a torque on the object. And the same holds if I rotate this object, you can work out for yourself that you'll get a net force on it. So rotation will produce a force. And since we're in Japan, I'll mention there are great papers from Doi, I'm sorry if I say this wrong, Makino, from the 2000s on these kinds of objects. So how can we express this mathematically? We could try to write complicated expressions, go back to the last slide, add more terms and so on. But I'm going to show you a formalism that takes care of this quite naturally. But before I do that, let me just introduce another situation, very common situation, where you get translational rotational coupling. So here I have a sphere that's translating near a solid wall. The fluid is very highly confined in this gap. So you expect a strong traction, i.e. force per unit area on the bottom, much stronger than on the top. In other words, you expect a very strong viscous friction on the bottom. So that will produce a torque on this guy as well. Translation produces or gives a torque. Kind of like rolling of the wheel of a car, but we have a lubricating gap here. We don't have contact with the wall. So how can we express this? Howard Brenner in the 60s came up with an excellent formalism that everyone in the field uses, the resistance matrix formalism. So we have a linear relationship between the generalized force, so forces and torques, and the generalized velocity, translational and rotation. And these coefficients tell you how forces and torques are related to the velocities. And you can compute this pretty easily. Well, there's a straightforward way to compute this. You have 6 columns, and each column represents a mode of motion. So the third column is translation in the z direction. So this is the force in x due to translation in z. This is the force in y due to translation in z. Force in z due to translation in z, and so on. So each of these columns they represent 3 modes of translational motion, 3 modes of rotational motion. And our rotational translational coupling is going to appear in these 3x3 blocks, off-diagonal blocks. So here it is stated a little more formally. We have the generalized force related to the generalized velocity. We have a minus sign there just by convention because we want the components of our resistance matrix to be positive. And actually, the resistance matrix has certain mathematical properties discussed in textbooks. For instance, R must be symmetric. I want to retract that statement, but there are some symmetries we'll see in R. R is positive, definite, and so on. So, by the way, I put in time dependence here. We saw that the Stokes equation is time independent. So it's a quasi-static equation, quasi-steady. So at any moment in time, if I know my velocities, then I can calculate my drag force and drag torque. So there's no history dependence here. There's no dependence on, there's no integral appearing here because the Stokes equation is time independent. Now let's look at those objects in the resistance matrix formalism. Sphere is very boring because it's spherically symmetric. So I get 3 identical diagonal components here, 3 identical diagonal components here for the rotational drag coefficient. And then I go to the spheroid, still pretty boring because diagonal, at least in its own, the frame coinciding with its axes. Then I look at a sphere near a wall. And this I computed with a library that you can download today. Professor Pazurkidis made this Fortran library, BEMLib. BEM stands for Boundary Element Method. Freely available. You can download it today and compute this resistance matrix. And you see now we have these off-diagonal terms here representing translational rotational coupling. I've also shown how these various terms scale with size. These off-diagonal terms go as r squared. So if you make the sphere twice as large, those things become 4 times as big. Okay. Now, one final thing with the resistance matrix formalism. Those resistance matrices, that were computed in convenient frames, right, that coincided with the axes of symmetry. You can always choose that frame, compute the resistance matrix, and then rotate the submatrices to the frame of interest. So if you had a spheroid near a wall, you could compute the resistance matrix in a frame coinciding with the spheroid axes and then rotate to a different frame. Each of these guys, each of these guys is a tensor and transforms like a tensor. R itself is a matrix, not a tensor. Well, these guys are matrix representations of tensors, I guess you would say. I know they're mathematical physicists here, so I want to be careful what I say. These guys transform like tensors. R itself is not a tensor. It's a matrix. So somewhere in the literature, I say resistance tensor, and I'm very ashamed to have that in print. So that's okay. I'm not the only person to have done that. Okay, so this is all very nice. So any questions so far? I'm going to move on to building up towards microswimmers, because the resistance matrix formalism will be part of developing a theory of microswimmers. Okay. So we know how to handle drag now. We have this resistance matrix formalism. How can I handle a microswimmer? So a microswimmer, as we already introduced, an interfacially active microswimmer is driven by a interfacial pumping, and it has some translational velocity, at least when it's axisymmetric. And we know that inertia is negligible, so we can say there's no net force on this guy. Well, linearity allows us to decompose the hydrodynamic force on this guy into a drag force, which we know how to do, and a thrust force, which is coming from the interfacial velocity. Because linear PDEs are linear in the boundary conditions, I can solve two different subproblems and then superpose the results to get the solution to this problem. So we know how to do this subproblem, and I will show you actually how we can get this thrust force fairly easily. So we have a very neat distinction, straightforward distinction between drag and thrust. This also holds for a mechanical swimmer. So this sperm swims by mechanical deformations, right? He's wagging his tail. There are waves of deformation going down the tail. We can also say that, although we might want to write an equation for torque as well. These guys instantaneously balance. Okay, here's the boundary condition for this mechanical swimmer. We have unknown translational velocity, unknown rotational velocity. So I like to think of this as this is the translational and rotational velocity of the head. And then in the frame of the head, co-moving with the head, we have deformation of the flagellum, which is prescribed. You expect it to be periodic in time. It's some prescribed deformation of the flagellum, or motion of the flagellum relative to the head. Right? So this stuff is going to give us the drag force, and this stuff is going to give us the thrust. So you get a quasi-steady relation between velocity, when you plug this stuff into the resistance matrix formalism, between velocity and thrust. This thrust might be difficult to compute, but you could compute it by keeping the head still and just, by saying these terms are zero, solving the Stokes equation for this term. Again, we're going to talk about how we might be able to compute that term more easily. One interesting thing here is, again, because Stokes equation is time independent, this holds for each instant of time in the periodic actuation of the swimmer. Of course, if you want to get the net displacement, you have to integrate this equation over one period. But knowing this, we can conclude something interesting. Why does the sperm have such a complicated tail motion? Why not just take a rigid tail and wave it back and forth? Suppose you did that. If you had a rigid tail and you waved it back and forth, and I'm going to distinguish a forward stroke in which the tail goes from here to here, and then a backward stroke where it goes from here to here. You can see, at least if the two strokes take half a period each, that the force in this instant of time, the thrust force in this instant of time will cancel the thrust force in this instant of time, because Stokes equation is linear, right? So I expect a minus sign relating the thrust forces in those two configurations. Now, you may think you're clever. You may think, okay, what if I do the forward stroke really fast and the backward stroke slowly? All that's going to get you is a fast forward displacement and a slow backward displacement, but the two displacements will cancel each other out because the Stokes equation is time independent. So if you're in this field, you know about this movie. You can go online, search for National Committee for Fluid Mechanics films. There are films corresponding to different topics. The one on low Reynolds number fluid mechanics has many famous demonstrations, and it's narrated by one of the most famous fluid dynamicists. I'm not sure if I want to play the sound because the sound is actually a little out of sync with the picture. But in this video, he does, let's see if I can find, he's going to contrast a swimmer with a rigid tail, that's this one, and a swimmer with helices. Again, chirality, wonderful for this workshop. And he'll show, I invite you to view the movie online, that the swimmer with a rigid tail can move in water effectively. But then when he puts it in glycerol, high viscosity liquid, he doesn't get anywhere. And then he's going to put in his helical robot and it will move, albeit pretty slowly. So that will happen shortly. Let's see, let's skip ahead to where he puts in the robot with two helical tails. The reason he has two helices, by the way, is to not get rotations. He wants this guy to move in a straight line. So he has a left-handed helix and a right-handed helix to cancel out the rotations on this thing. And he does effectively move. So if you're in this field, you've heard about the no scallop theorem, very famous theorem that some swimmer with a time reversible actuation can't go anywhere in low Reynolds number in very viscous fluids, or if he's very small. And this scallop theorem was worked out by Purcell. He has a very nice article I encourage you to look up, Life at Low Reynolds Number from 1977. Okay, since this is a chiral workshop, and not in this, but I'm not in this, but this is a chiral workshop, I'll bring back the helix and ask, how does the helix allow us to evade the no scallop theorem? Well, helix has handedness. It doesn't look the same when we rotate it one way or the other. It doesn't look like a time reversible motion. And if you work out the force balance in each segment, the key to the helix motion on a dynamical level is the anisotropy of drag that we've already seen, that a rod has much higher drag coefficient in the orthogonal direction or perpendicular direction than in the parallel direction. So if I have this helix rotating rotational velocity omega, this segment is instantaneously moving downward. I can decompose that velocity into tangential and perpendicular components. This guy is going to give me a big contribution to drag. This guy, a small one up there, F parallel. The resultant is that green arrow. And as I look at different points in the contour, I see that the Y and Z components of the green arrows will cancel out when I integrate over the contour, but I'll have a net force in the X direction or negative X direction when I integrate down the helical contour. And you can work out the force per unit length, or the total force, and its maximum when you have a pitch of 45 degrees and so on. If you're interested in this field, this is a really nice paper by Purcell where he had wires and he just had wires wound as helices and dropped them in viscous liquid and looked at their sedimentation. These days, I think people are starting to do 3D printing of different shapes and watching them sediment in viscous liquid. And I keep encouraging my students, why don't you 3D print something interesting? Nobody ever wants to do it, but it may be an interesting thing for you to do. Okay. But I'm not really going to talk so much about helices. I'm going to talk about ciliated microorganisms and synthetic Janus particles. So that offers, okay, if you're a ciliated microorganism, that offers another way to evade the scallop theorem. So this is a cilium executing a periodic motion. And you see there's a power stroke where the cilium is extended very far out and a recovery stroke where it's bent in towards the body of the microswimmer. So the elasticity of the cilium is crucial in breaking the time reversibility of that stroke and giving you net pumping over one period. So looking at this, you expect fluid to be pumped to the right, and that's correct. Now, you don't want to just have one cilium. It's not going to give you much power. You want a lot of cilia. And if you want to pack a lot of cilia together, well, you have to coordinate their motion so they don't crash into each other and tangle and so on. So that's why these microswimmers are coated with a carpet of cilia that beat in a coordinated fashion. And that coordination looks like a metachronal wave going down the tips of the cilia, and that gives a net pumping to the right. So this motivated the Squirmer model. I'm going to give you my oversimplified version of it. The original papers are from the 50s and also in the 70s by Blake. This is my favorite model for low Reynolds number fluid mechanics because I think it's the easiest to do theoretically and also computationally. So if you want, we can talk about how to do this computationally, put it in your favorite fluid solver and so on. This is not the first model for a microswimmer, by the way. I think Taylor's swimming sheet was first, but I think this is the easiest. I like this one the best. So we have the ciliated microorganism. Let's treat it as a sphere. It's coated with these small cilia. They're waving periodically. And we look at this and we say, well, the amplitude of these, the length scale of the cilia motion is much smaller than the length scale of my swimmer. So I have a separation of size scales, A over L. And let's say our swimmer is also very slow. So you get many periods in the time it takes this swimmer to move one body length. So we have a fast time scale, the time scale of the waving, and we have a slow time scale, the time scale of displacement of this squirmer. Well, in that case, we have a separation of time scales. We can treat this unsteady problem as being an effectively steady problem. We're going to neglect the time variation of the interfacial flow and treat that as a steady interfacial pumping. So we're no longer resolving this complicated geometry. We're just having a sphere, and we're no longer resolving the unsteadiness of this. We're just going to have a steady interfacial flow. So this is the model you get. We have the Stokes equation governing the fluid around the particle. Again, we're doing incompressible flows. Far away, the velocity is 0. And then here's where all the action is. On the surface of the swimmer, we have an unknown translational velocity, and we have some specified steady tangential velocity, which I'm going to treat as axisymmetric for convenience. Finally, this is a very important condition. Swimmers swim without the application of external forces. We already saw that 0 equals F drag plus F thrust. So this gives you the force per unit area on the swimmer. Here, sigma is the stress tensor. I integrate this traction over the surface, I get no net hydrodynamic force. If you want to put in an external force like gravity, it's very easy. It's just by linearity, you can compute that separately and superimpose it. Okay, so far so good. Okay, it will turn out to be a clever thing to do to write your slip velocity, which can be whatever you want. If it's axisymmetric, to write it in terms of these so-called squirming modes. We'll see where they come from. It will turn out to be a clever thing to do. And these squirming modes are basically associated Legendre polynomials, so they are complete and orthogonal basis for the interfacial velocity. So whatever US you give me, you can always find a unique spectrum of squirming mode coefficients Bn, where we get B1, B2, B3, and so on. Alternatively, if you don't give me this function, you can just specify directly B1, B2, B3. A lot of people do that in this literature. They just simply say, okay, B1 is something, B2 is something, and they go from there. Well, this can also be used to model Janus particles because we've coarse-grained away the cilia. We just have this steady interfacial pumping. So if you can obtain this function for your Janus particle by whatever propulsion mechanism you have, then you're set to go with the Squirmer model. Okay. All right, how are we going to solve this? I mean, Stokes equation is still a vector PDE. You could go about and try to solve this directly using the stream function. Math gets kind of nasty. I'm going to show you there's a simpler way to get the velocity, which everyone in this field likes to use. It's called the Lorentz reciprocal theorem. It's this wonderful theorem in low Reynolds number fluid mechanics, and there's something similar in electromagnetics, and maybe you've seen something like this, where if I have Okay, let me unpack this. The Lorentz reciprocal theorem relates the fluid stresses sigma and sigma prime and velocity fields u and u prime of two solutions to the Stokes equation that share the same geometry. Well, this is the Lorentz reciprocal theorem. You see that we have one prime appearing here on the left-hand side, another prime appearing on the right-hand side. There's some kind of juggling around of u's and sigmas there. So here's the idea. We have this wonderful theorem. The textbook will derive it for you. Let's use it, and let's use, for the unprimed problem, the problem we want to solve, the Squirmer problem, and for the prime problem, let's use something for which we already know the solution, or for which we can look up the solution. I said I don't want to solve the for Stokes drag law, but it's something available in textbooks you can look up. So let's use that. Here's my application of Lorentz reciprocal theorem. This is the problem we gave, the squirming problem. We don't know what the velocity u is. We know what the us is. That's specified. And on the right-hand side, we have a translating sphere as the prime problem, translating the velocity u prime. The solution for this is already available in your favorite fluid mechanics textbook. And I'm going to do this all in free space and no boundaries or anything. You can always apply to boundaries, but for simplicity, I'm doing this in free space. Okay, so I invite you to download my slides and work this out at home. The math is actually not that hard. And if you work out this math, if you had worked it out in 1996 and some other things, you would have gotten a PRL. Of course, you had to have had the idea to do this in 1996. That's the challenging thing, not the math really, but you can work out the math. I'll just point to the right-hand side. On the right-hand side, we have u prime dotted with sigma dotted with n hat ds. Well, this is on the boundary of the swimmer S. And the prime problem is the translating sphere. So for the translating sphere, u prime is equal to big U prime, which is a constant on the surface of the sphere. So we can pull that out of the right-hand side, and you just get big U prime dotted with the integral of sigma dot n hat. Well, what is the integral of sigma dot n hat ds? This is where you're integrating the force per unit area over the sphere in the squirming problem. We already said microswimmers swim without the application of external forces, so there's no net force, no hydrodynamic force on the swimmer, and it's 0. So the whole right-hand side works out to 0. And you can work out the left-hand side. You just plug in this stuff. This is from a textbook, rearrange, and lo and behold, what did you get? You get, here's the drag force, which we already discussed, Stokes drag law, and then here we've gotten the thrust force. Drag plus something is 0, well, that something must be the thrust. So I've shown you how, at least in this case, we can obtain the thrust force without solving complicated PDEs. Okay, I'm not going to work through all this stuff. It's in the slides. You can download them. If you apply to a squirmer, you just plug in, whoops, sorry. This is forward, okay. If you want to apply to a squirmer, you plug in your US. And we want to get the Z direction, so you dot with Z, because it's axisymmetric. Then you plug in, well, our interfacial velocity is given in terms of squirming modes. You plug that in, you work out the math. The nice thing is that the squirming modes are orthogonal because they're associated with Legendre polynomials. So when you work out the math, at the end of the day, you get that the velocity is 2/3 times B1. And now you see why these squirming modes are so useful, because only B1 contributes to the velocity. B1 controls the velocity of the squirmer. Well, the other squirming modes have a role to play too. If you go further into this, you will find that this is what the flow field looks like. And you see all the squirming modes contribute. This is in spherical coordinates. And actually B1, which is here, is not giving you the slowest decaying mode. The velocity contribution of B1 decays as 1/r². And then you go over here, and you see that the velocity contribution of B2 decays as 1/r², more slowly. So B2 also has a special role because it gives you the slowest decaying contribution to the flow around the squirmer. So B2 is very important because if you want to understand interactions between squirmers mediated by the fluid, you want to consider B2. By the way, where do these come from? Stokes' equation is separable, but it being a vector equation, it's a little hairy. There's something called Lamb's general solution, which you can find in textbooks. And this is basically the axisymmetric case for Lamb's general solution when you separate Stokes' equation. Okay, so this is what you get for the flow fields. And generally in this literature, people truncate the squirming modes to B1 and B2. Why? Because B1 gives you the velocity, B2 gives you the slowest decaying contribution to the flow. So let's just forget about the rest. And these are characteristically what you get for different ratios of B2 and B1. So in this literature, you hear a lot about neutral, pusher, and pooler. Well, there it is. So if you have B2 is 0, then you only have a B1 mode, which is unbiased between the front and back because theta ranges between 0 and 180. So we have sine going between 0 and 180. It's nice and symmetric around 90 degrees. There's 90 degrees, it's the equator. So the B1 mode is unbiased between the front and back in terms of the interfacial velocity. So that's why it's called neutral. It doesn't favor the front or back. And you get this kind of dipolar flow when you just have B1. By the way, I like to think about this dipolar flow as originating in mass displacement. So as this squirmer moves through fluid, it has to push mass out of the way, and it's vacating the space behind it. It has to suck mass into that space, and that gives you this dipolar form. So given by mass conservation. But when you put in a B2, you get rather different flow fields. If you put B2 over B1 as 5, a positive number, then you're biasing the slip towards the front because we have a 2 theta here. So for theta between 0 and 90, we'll get positive. For theta between 90 and 180, we'll get a negative number. So we're enhancing the slip in the front and decreasing the slip in the back. That gives you what's called a pooler because all the actuation, the interfacial pumping, is towards the front of the particle. Hence, name pooler. It's pooling itself through liquid. Conversely, if you have a negative ratio, then you're enhancing the slip in the back. So all the swimming actuation is in the back. It's like it's pushing itself through liquid. And you see that these flow fields, they tend to have flow coming out of the poles. For the pusher, it's coming out. For the pooler, it's being sucked in. And then for the pusher, we have flow coming into the equator. And for the pooler, we have flow going out of the equator. Okay, so I have 30 minutes left, not nearly through my slides. That's fine because I've given you the squirmer model. Any questions so far, comments? Yeah.
Maybe it's you have in the other slide, but I was wondering if you now apply, because you talk about rotation also.
Yeah.
If we want to make like comparison with the penguin can change direction when he wants, but when you have an object like this, is more like a bullet.
Yeah.
So is any example of circular motion that use angular momentum conservation to keep the direction?
You are 3 slides ahead of me, I think, because
Sorry.
if you give, no, good question. If you give an azimuthal contribution to the slip, it will rotate in the opposite direction. So if you work out the details of this azimuthal, maybe you could do Lorentz reciprocal theorem for using the, as your auxiliary problem, your prime problem, a rotating sphere. That's probably how I do it. You can show that this azimuthal slip will give you a rotation. And of course, if 2 squirmers are near each other, they interact and they will change their directions. They may rotate towards each other, away from each other, depending on whether pushers and pullers. So a lot of literature on that interaction, pairwise interaction. Any other questions, comments? All right, so you may ask about extensions of the squirmer model. So one thing we did back in 2020 was look at spheroidal squirmers, whether prolate or oblate, we developed a complete and orthogonal set of squirming modes for this. Little hairy in that Stokes equation is only semi-separable in spheroidal coordinates, but you get something interesting. It's that swimming is not only driven by B1, but also by all the other odd modes. So if I have a B3 mode, that will also contribute to the velocity as shown here. So here are the contributions of the different modes to the velocity. You see B1 contributes the most, but B3 contributes something, B5, etc. And this is for different aspect ratios. So as you make it more sphere-like, these higher order contributions go away. Again, you see this nice dipolar form with B1, but B3 has these interesting vortices. So maybe this is important for the swimming of elongated microorganisms, that they can swim and generate vortices. Not so many people have looked at oblate. We're going to see oblate as something really interesting. And the reason people haven't really looked at it is, I think, because biological microswimmers generally look like that and not like that. But you can do the same thing for oblate and you get the same result, that the different modes can contribute to the velocity. Now, this is a chirality workshop. And we already had a question, how can I make them rotate? Very easy, you just give an azimuthal slip. Now, this paper came out 2023. We just read it in my group. And it's about chiral microswimmers and how they synchronize. And honestly, I wish I had thought of this. This is such an easy way to make your swimmers chiral if they're spherical. It doesn't work for spheroids. But if you have a spherical microswimmer, they consider in this paper 3 modes. So the B1 we talked about already, this azimuthal C1, which will make it rotate. And then they have this B tilde 11, which is just this rotated 90 degrees. So it will give you a velocity in the Y direction instead of the Z direction. Very simple thing to do, because if you superpose them, say you superpose these two guys, this guy will be swimming along this axis, but you're continuously rotating the particle. So you'll get a circle swimmer, which are a very big deal right now in active matter, circle swimmers. They give you all sorts of interesting things. And so I would say these particles are chiral in 2 senses. One, you have this chirality in their slip, and then you also have chirality in their trajectories, and those things are related. If you have all 3 modes, you'll get helical trajectories. And they get interesting things in this paper, synchronization of their circle trajectories and so on. So very clever. I wish I had thought of that. One thing to do might be to look at chiral spheroidal squirmers, but I think that's going to be a little more complicated because no one has combined spheroidal squirmers and chirality in the slip. So a lot of people looked at squirmers with non-axisymmetric slip, including that paper, that makes them rotate, but no one has looked at these things together. And why is that interesting? Because shape really matters in the interaction of microswimmers. You see that these 2 prolate spheroids are forming a bound state, and the shape is very important to that. Okay, what about Janus particles? Way back at the beginning, I talked about Janus particles. All you have to do to apply the squirmer model to Janus particles is get the surface flow from some model, and you see that this is a very, very simple model for the concentration field. So this is the simplest model for a chemical swimmer one can think of. The concentration field is governed by Laplace equation. The cap is emitting solute at a constant rate per unit area. And the inert region is impenetrable to solute, to the reaction product. You can solve this easily. You can get the slip and then feed it into the squirming problem and get the velocity in the flow field. Of course, there are variations on this. You can always make it more complicated, but this is the simplest model that was developed by Golstani in Liverpool and Ashdari in 2007. By the way, this B depends on the material composition. So this is kind of the responsiveness of the particle to tangential concentration gradients. That's controlling the magnitude of the slip. And you expect this B to be different between the 2 faces. That gives some interesting results. So you can plug it into the squirmer model. I won't go through the details. You can download my slides and check it out. We have a whole paper about Janus particles as effective squirmers. Okay, and here are the Janus particles and the flow fields around them. They have the same concentration field. The product is being generated on the cap in both cases uniformly, but they have different phoretic mobility coefficients. So here, both sides respond equally to tangential concentration gradients. So it's like a neutral squirmer, not biased between the front and the back. On this side, I only allow the cap to have a slip velocity, to have an interfacial pumping. And you see this looks a lot like a pooler. Quality is not so good, but you see that we have fluid being pulled in to the front and ejected from the sides, like with the pooler squirmer we saw already. If you want to do this in 3D, again, if you want to have rotations, maybe you have a particle near a surface, so it's going to, you don't have axisymmetry anymore, you expect it to rotate. This whole formalism can be applied to 3D, but you have to set up 6 auxiliary problems corresponding to the 6 degrees of freedom of the particle. It's worked out. We work out the details here. You again get the thrust force plus the drag force is 0, where the drag force is handled through the resistance matrix formalism, and the thrust force is computed by these integrals. You can get the 6 components of the generalized thrust through these integrals involving the interfacial velocity, the surface slip. Okay. All right, for the remainder of the talk, as far as I can, I'm going to talk about interactions between swimmers and how to model them approximately and analytically. Right, and for that, I need to go back to the Stokes' law problem that I'm trying so hard to avoid doing because it's very long. So I'm just going to give you the solution from the textbook for a translating sphere. So this is the velocity field in spherical coordinates for a translating sphere. It's translating with velocity u. And if you integrate the surface stress and pick out the z component, you get Stokes' law. So this is what I have avoided working out. The interesting thing here, though, and this is what I want with this, is what if we take the sphere size to go to 0, but keeping the force to be fixed? Keeping the force to be fixed, so I could re-express u as FD over 6 pi mu r. And some magic happens, because here I'll get FD over 6 pi mu r. Over here I have 1 factor of big R. Those will cancel out. So as I take big R goes to 0, shrink the sphere to a point, this term will survive, and this term will survive. These terms will go away because they're due to the finite size of the sphere, representing again that the sphere must push fluid mass out of the way and suck it back into the trailing edge as it moves. But as you take big R goes to 0, you can have these survive, and that gives you the solution for a point force in the z direction. What is that? The solution for a point force. It is the Green's function for Stokes flow. I give a Dirac delta forcing to the PDE, I get the flow from that. That's the Green's function. So this is this is my favorite way to get the Green's function for Stokes flow. And this is what the Green's function looks like in a coordinate-free form. Everyone in the literature uses this form because it doesn't assume that the force is in the z direction, and nice and coordinate-free. And this, you see that the velocity is linear and the force as we expect. The force is applied at position x naught. It decays as 1 over r, very, very long ranged in 3D. And this big quantity here is called the Oseen tensor, sometimes defined without the 8 pi mu, but this tensorial coefficient is called the Oseen tensor. And so there's a lot of fun you can have with this. I don't have time to talk about it, but because this is so long-ranged, a lot of interesting things happening in collective sedimentation. This was a big topic in the 2000s and 90s. What happens if you have a lot of spheres falling together? Well, this is very long-ranged in 3D, right? Divergence. So interesting things happen there. One thing you can do in a classroom is if you have 2 spheres falling together, you can work out the details. They'll fall faster than one individually. You can see they're kind of generating flows that carry each other downward. Moreover, if they're identical, they will not have any relative motion. That's actually coming from the symmetry in x and x naught in this osine tensor. If you exchange x and x naught, because we have two factors here, we get the same expression, right? The minus signs will cancel out. So we're symmetric in x and x naught. So two identical spheres will show no relative motion if they're falling together in free space or unbounded fluid. They will, however, drift relative to the direction of gravity. You see that they're both pushing each other to the right, or they're creating flows that carry each other to the right. So they will show a lateral drift in addition to motion downward. Kind of fun to do that. If you have three spheres, by the way, there's a famous paper, 1997 by Tell. The motion of three spheres is chaotic. Very fun paper to read. I'm going to skip this. I have 20 minutes left. So I'm going to get towards more advanced stuff for modeling swimmers. And it's going to be based on these hydrodynamic singularities or Green's functions. And we know a swimmer is force-free, right? So I cannot have a Stokes slit. I cannot have a point force in how I model a swimmer. However, I can have two equal and opposite forces. There's no net force here. So I'm simply superposing two point forces. And this is going to give me the velocity field by linearity. And I can do some Taylor expansion on the second argument here and just keep the first term that survives. And I get this approximate expression that we're going to see on the next page. So we're going to make a higher order singularity by shrinking this d to 0, having a point force dipole. Right now they're separated by a finite vector d. We're going to shrink that to 0. If you do that, well, okay, as you work out this Taylor expansion the first order, this is what you get. Actually, it looks pretty reasonable. It decays as 1 over r squared, as you might expect. If I take a derivative of something that decays as 1 over r, it's going to decay as 1 over r squared. And that's looking like already like our B2 mode, right? That generated velocity that decayed is 1 over r squared. At this point, this is conventional in this literature. You define this tensor D, which is the outer product of f and little d, with a minus sign by convention. It's convenient to do index notation, so this is what you get with this D tensor. Okay, we're almost there to the good stuff. You take this tensor and you write it in this way. This is the trace, 1/3 of the trace times the identity tensor. The reason you pull this out is that it does not contribute to an incompressible flow, so we just want to pull it out and forget about it. But these two things are very interesting. The first one is called the stresslet, and it's symmetric in the two indices, and it's a nice bona fide tensor. And we'll also see this guy. This is going to be the, I guess he called the Rotlet tensor. This is going to be related to chirality later. But for now, I'm going to focus on this. If you plug this into our velocity field in an index notation, you get a very, very simple expression. This is the velocity field due to the stresslet, i.e. the symmetric part of the point force. Looks very nice, I think. And so this is the leading order flow from a force-free and torque-free microswimmer. We'll see in a little bit, this is actually representing a point torque. So we don't want that for a microswimmer, but we will want that for rotating magnetic colloids. So this is what you use to represent interactions of microswimmers. Now, most people in this literature, they consider axisymmetric stresslets. So they have a thrust force and a drag force that are collinear, and they're separated by some distance. That's the little d. The reason the thrust is pointing towards the swimmer is because we're showing forces on the fluid from the swimmer. So the drag is in the direction of motion. The thrust is opposite the direction of motion. And you see the thrust here is in the direction of the swimming motion. So this is a puller. Here, the thrust is behind the direction of motion. That's a pusher. And biologically, a puller could be a microalgae, and which have two big flagella at the front. And a pusher could be a bacterium that has a rotating helical flagellum at the back, or bundled flagella. And people like to write this, David Santillan does a lot of this, and Michael Shelley, they like to write this in a nice coordinate-free form, which is axisymmetric, traceless, and the sigma naught quantifies the strength of this force dipole and discriminates between pushers and pullers. So I think sigma naught is positive for a puller and negative for a pusher. And we have the swimmer axis of symmetry here, nice and thematic symmetry, by the way, for you liquid crystals guys and girls. So people use this in the literature a lot. This is what the flow field from an axisymmetric stresslet looks like. And you can compare with the pusher and puller squirmers, very, very similar, but not identical. Because for the squirmers, we account for finite size. This is a point force dipole. So we don't account for finite size here, but otherwise very similar in the far field between these pictures. One thing, okay, getting back to our research, one thing we noted is that not all active colloids are axisymmetric in their slip velocity, in their actuation. So going back to the metallodielectric Janus particle in an E field, AC electric field, if you plot the slip on the metal side, the interfacial flow, this is not axisymmetric. It's tending to go towards the equator, and it's 0 on the equator. So not axisymmetric. This is a discoid, by the way, so this is not a sphere, but the axis of the disk is kind of into the page, and this is the metal side. So that's something we noticed. And actually, it's very, very important because we worked with Jaideep and Alex Nezko at Argonne, and Jaideep could make these disks, and he makes them with a nanoscribe. So the white is SU8, and then he deposits metal. So the brown is gold, I think. Doesn't matter, it's some metal. When you put them in an AC field, they stand up, and they start moving away from the metal side. So with the field off, they look like disks. With the field on, they look like grains of rice that are moving on the short axis. And he sees something very, very interesting, that these guys form bound pairs. Many, many bound pairs that have very low motility because they're facing each other. Two particles in a bound pair are facing each other, so they're not moving very much. And we have the singletons moving around. Eventually, they find a partner. Inspirational, I guess. Okay, never mind. We'll go down that road. But you have many, many bound pairs, and this can actually lead to phase separation under some conditions. So we sought to model that. And when we modeled it, we did the full gory electrokinetic model for ICEP for these electrokinetic swimmers. And we got this pairing behavior as seen in the experiments. So that was nice. This is what the pairing looks like on a two-particle level. You see these two guys are coming in slightly off register, and they rotate around each other. And as they rotate around each other, they slide into register, so there's no longer any offset. So that's the kind of thing we could get in our model. But our model was very, very complicated. So we wanted to look at this purely on the level of hydrodynamics. So we looked at the spheroidal squirmer, and we added a mode that's non-axisymmetric. So we have the B1 and B2 modes for a spheroid, oblate spheroid, but we came up with this non-axisymmetric mode because the slip velocity, as we saw, is not axisymmetric. And this mode breaks the axisymmetry of the stresslet. So this is what I showed you before that David Santillan, Michael Shelley, everyone uses for an axisymmetric swimmer. This term is breaking axisymmetry. It's controlled by this mode. Linearly, this delta parameter breaks axisymmetry. It's linear in this B tilde mode that we came up with. And this is what we get. Actually, we have two essential ingredients to get bound pairs. We need to have a discoidal shape, so spheres won't do it, and prolate particles won't do it. Have to be discoidal, and we have to have this non-axisymmetric slip. So that's a delta parameter They can't be axisymmetric swimmers. And we get this, we had kinetic theory that gave us this theoretical boundary in the background color. And we did BEM high resolution simulations that gave us the symbols, and they agree pretty well. So I think one frontier is non-axisymmetric slip, including chirality. So these particles are achiral, by the way. They're not spinning. What happens if we added chirality, made them spin? Maybe interesting things. I would like to work on that. We only have a few minutes left, so I'm going to talk about something very chiral. We had also this piece of the D tensor. Remember, D was negative FD for the negative F little d for the point force, or it's a force dipole. This was the anti-symmetric part of that tensor. You can work through the math, and you can show, using this identity, that the flow field due to this is the same as a flow field due to a flow field around a spinning sphere, a sphere driven by an external torque M. And the sphere size does not appear in the equation, so we can interpret this as the flow due to a point torque. And as very, very simple form, decays as 1 over r squared. This is an interesting thing. These are two spinners, and this is the flow due to a point torque. Well, we have 2 point torques here, or 2 external torques acting on each spinner. So you can expect from this that they'll rotate around each other, and that's what they do. They rotate around each other. And this is all with that resistance formalism that I discussed earlier, all done with that BEM-lib library that you can download, thanks to Professor Pazarkidis. To get the velocity at every time step, you just compute the resistance matrix, invert the resistance matrix, multiply by the generalized force, which includes the torque on each swimmer. Now, this is without magnetic dipole-dipole interactions. If you put in let me flip back to this. If you put in dipole-dipole interactions, they'll be attracted, and you'll get decaying orbits. They'll crash into each other. In the couple minutes left, so Jaideep, my collaborator, made hematite particles. So they have a permanent dipole moment, and he put them in a rotating magnetic field. And when you do that, these guys spin and they form clusters. And these clusters grow over time. This is something that was known in the literature before. Very interesting topic. And these are actually chiral fluids because these guys are rotating and each cluster has an edge current. So this is showing the edge current of a cluster. You see the core of a cluster is rigid, or the particles are not moving, but around the edges, the particles are moving in a circle. This is the magnitude of the velocity, and he's showing the vorticity. So we get these chiral edge currents, very well known in active matter for circle swimmers and chiral, for chiral active fluids. What Jaideep did was he added chemical activity to it by, these hematite particles, they can decompose hydrogen peroxide if they're exposed to UV. So it's photocatalytic activity you can control with UV light. When he turns on the UV, the clusters loosen and the edge currents are suppressed. And this is reversible. When you turn the UV off, you turn the chemical activity off, the clusters tighten up again, you get the edge currents reemerge. So our side was to model two particles. Again, they crash into each other if you just have magnetic and hydrodynamic interactions. When you add the activity, you can get the particles staying apart in a bound state, never touching each other. So that's one potential explanation for this. Activity repels the particles, but keeps them together so the cluster doesn't break apart, but it loosens up. So we have these bound states where particles don't touch each other, but they also don't move away from each other. Last slide, I think. So I talked about rotlets, point torques, but we cannot have a point torque for a microswimmer. You asked about swimming microswimmers. How can we represent that with these singularities? Well, you take a point torque and look at a dipole of 2 point torques. equal and opposite, no net torque. And this could represent a bacterium with a head rotating one way and the tail rotating the other way, for instance. No net torque, two counter-rotating pieces. Or it could represent a spinning microswimmer. And here in Japan, Sano group, this is really, really lovely work. They have these chiral liquid crystal droplets. This is with the cholesterolic, sorry, you guys are liquid crystal guys, mesogen, cholesterolic component, and this is with a pneumatic component. These guys show that Bartlett dipole flow. You see down here, the direction of rotation is one way, and the other side, it's the other way. You get clockwise and counterclockwise on the top and bottom. So they were the first people to measure this Bartlett dipole type flow. Okay. Final two slides in the last 2 minutes. These singularities also you can use to model, if you want to model a boundary, you may know from electrostatics about image systems. You can do the same thing with these hydrodynamic singularities. You build an image system that enforces your boundary condition on the boundary. This is a very famous one, the Blake slit worked out by Blake in 1971. This is important for bacteria. Again, I said these two pieces of the bacterium are counter-rotating, so there's no net torque, but there is a Bartlett dipole, two point torques in equal and opposite direction. This gives rise to circle swimming of bacteria when they're near solid liquid boundaries or air-water boundaries. The senses, when viewed from above, I think are different between these two types of boundary. So that was a big contribution of Eric Lauga in 2006, understanding the origin of circle swimming in the hydrodynamics of the interaction of this with a boundary. All right, that brings me to the end. I just want to point out two future directions for active colloidal hydrodynamics involving chirality. There are two related aspects of chirality I perceive: spinning of particles, but also relatedly circular and helical trajectories. Magnetic spinners are active chiral fluids. We could look at the shape of the effective particle shape, activity, and so on. And I would like to look at spinning microswimmers. They have no net torque, but they have a Bartlett dipole. How does that affect their pairwise interactions? What is the phase behavior of spheroidal chiral squirmers? All right, so as we say in Hawaii, mahalo. Here's the link to the slides. I have 2 minutes left if we have any final questions.
Thank you for this wonderful tutorial lecture. Do we have questions?